Hey there, STEM Chemistry. This is Missouri Arc. This is podcast 6.2, where we're going to talk about how do we use stoichiometry. Now, you got a little taste of it in the last one, but we'll just kind of dive in a little bit more. All right, so the balanced chemical equation for producing water is as follows. You have two waters, that was cute, two hydrogens and one oxygen, and they come together in the perfect combination to form two waters. Okay, so we cannot say that 2 grams of hydrogen combine with 1 gram of oxygen to form 2 grams of water. The reaction here is describing moles or particles. So many stoichiometry problems are going to follow a pattern. You might want to write this pattern down. Okay, so you'll have grams of a certain substance. And those grams of a certain substance will change into moles of that same substance. Notice how X and X. And then we'll go from moles of that substance to moles of a new substance. Notice how it's changed to Y. And then we can change from moles of Y to grams of Y. Now this is the typical pattern that they would follow. It's not the only pattern. This is when you're going from grams to grams, mass to mass. You can also do it where you're going from volume to volume, grams to volume, or liters, moles to liters. You know, there's tons of different ways to do this. And then when we get into solutions, we'll be using the molarity of a substance to find something else. So there's tons of ways to do stoichiometry. Don't think this is the only one. You probably want to write this down. Write this down. Oh yeah. Okay. I went too fast. Sorry. All right, so let's just jump right in. For the reaction, 2 hydrogens plus 1 oxygen gives 2 waters. What is the path we would take for the following? So if we were given 2 moles of water, how would we calculate grams of water? All we're doing here is setting up the work, like set up the work. Okay, so we would have 2 moles of water. And if you think you got this, actually it would be best if you go ahead and pause it and then come back and check your work anyways. All right, so 2 moles of water, we're going to go from moles of water. We need to get rid of moles of water. And we need to change to moles of, nope, sorry. We're going from moles of water to grams of water. So this needs to be grams of water on top. Okay, number with moles should be 1, and then the number here would be your molar mass, 18.02. Okay, and then you would have your moles cancel, and you would do your math. All right, so what if for letter B it says moles of O2, how many moles of O2, that's what we're looking for, required for 36 grams of water, of hydrogen. So if we had 36 grams of hydrogen gas, we want to get rid of hydrogen gas, so we're going to put grams of hydrogen gas on the bottom. Now, we can't go from hydrogen to oxygen. We can't do that unless we are in moles and moles. So we have to change this into moles. And if you're unsure, let's go back here and look. Remember? Grams, moles, moles, grams. Okay? If you're still kind of like, what is she doing? Well, we have grams of X to moles of X. Oops, to moles of Y, to grams of Y. And I'm going to use the abbreviation. Okay, so we're at moles of oxygen, and we've got to go to grams of hydrogen. So we're actually here at, we're at grams of hydrogen, and we've got to go to moles of oxygen. So we're starting here at grams of X, and we're going to end up at moles of Y. There's a path that we're following, right? So we've got to go from grams of hydrogen to moles of hydrogen. And then this would be 1 and this would be 2.02. Grams of hydrogen cancel. But we're not done. We want to get rid of moles of hydrogen and we want to find moles of oxygen. Okay, well, what numbers go here? Remember, this is where your mole ratio comes into play. Mole ratio comes from your balanced equation. So 2 goes with moles of hydrogen and 1 goes with moles of oxygen. Moles of hydrogen cancel, and we're left with that for our answer. Okay, what if we had grams of water, or how many grams of water, so that's what we're looking for, produced from 6 grams of O2. So look, we're going from grams of one thing to grams of another. So we're starting here at the beginning and we have to go all the way through to the end. So we start with 6 grams of O2. We've got to go from grams to moles. So we've got to get rid of grams of O2 and we go to moles of O2. This would be 32.001. That cancels. Okay, now we're going from moles of O2 to moles of H2O. So we put moles of O2 on bottom, moles of H2O on top, mole ratio. Right, so this would be a 1 and this would be a 2. And then we go from moles of H2O to grams of H2O. 1 and 18.02. And there you go. That's all you got to do. This is stoichiometry, boys and girls. Yay! I know you like that word. Okay. How many moles of H2O can be made using 0.5 moles of NH3? We've got a balanced chemical equation here. I know Miss Rook was nice. She gave you a balanced chemical equation. All right, so we're looking for moles of H2O, and we're using 0.5 moles of NH3. So for letter A, 0.5 moles of NH3. Sorry about that. And we want to get rid of moles of NH3 because we want to go to moles of H2O. What numbers do I get here? Well, I pull them from the balanced chemical equation. We've got 4 and we've got 6. Right? So now we do the math. We're actually going to do the math on this one. So we've got 0.5 times 6 divided by 4, and that gives us 0.75 moles of H2O. So we would need, we would make 0.75 moles of H2O by using this many moles of ammonia. See how easy that is? All right, what mass of NH3, so we're looking for grams, is needed to make 1.5 moles of NO? Well, it doesn't matter if this is on the reactant or the product side. We're still starting with that number. So 1.5 moles of NO. All right, we want to get rid of moles of NO and we want to go to grams of NH3. So we have to go from moles of NO to moles of NH3. Okay. Well, in our balanced chemical equation, we have a 4 for NH3 and we have a 4 for NO. Yay, that's easy. 1-to-1 ratio, right? Okay, so moles of NO cancel. We're left with moles of NH3, and we've got to get to grams of NH3. So we put moles on the bottom, and we put grams on top. And then to get the answer, or the mass for that, we do 14 plus 3, so 17.04 grams. Moles cancel. And so now we do 1.5 times 4 divided by 4 times 17.04. And we get 25.56 grams of NH3. All right, so going ahead and try letter C. Let's see if you can get that, okay? And I want you to bring it with you to class. Okay, here we have letter A, balanced chemical equation. What mass of O2, so we're looking for grams of oxygen, will react with 400 grams of C4H10, that's butane. Butane. All right, so to solve this, we start with our 400 grams of butane. Right, 400 grams of butane, and we need to go from grams of butane to grams of oxygen. So we have to go from grams to moles to moles to grams. So we're going to put grams of butane at the bottom, moles of butane at the top. Okay, and that would be 1, and then we need 12.01 times 4 plus 10.10 gives us 58.14. Right, but we're not done. Now we need to go from moles of butane to moles, of oxygen. So we have 13 and 2. Right, we got those from here, 13 and 2. All right, now we're not done. We got to go from moles of O2 to grams of O2. So 32.00. Why? Because there's 2 of them and 1 here. All right, now we can solve. So 400 divided by 58.14 times 13 divided by 2 times 32. And we will get 1431.02855. Oh, I went off the screen. Sorry. Okay, but we only need one significant figure, so we're going to round this to 1000 grams of O2. Or you can write it in scientific notation, your choice. Okay, on letter B, what volume of carbon dioxide is formed? What? All right, so we're looking for volume of carbon dioxide. So we're going to start, and we can start with, I would go back and start with this number here. So we're going to start with 400 grams of butane, and we're looking for liters volume, right, of CO2. You know how to do this. Okay, so we're going to start with 400 grams of butane. We multiply it and change it into moles. So we put grams of butane on the bottom, C4H10, moles of butane on top. Because remember, whenever in doubt, go to moles. And then from moles, you can probably figure out where you need to go. All right, 58.14 grams on the bottom, 1 mole on top. That's going to cancel. All right, so now can I change from butane to CO2? Yes, I can. I can use my mole ratio to go from butane to CO2. Okay, so what's my mole ratio? Well, it's a 2 to 8. So 2 and 8. All right, so now we're at moles. Can we go from moles to liters? Yes, you can. All right, so moles of CO2 is equal to how many liters of CO2? Remember, because this is a gas, we can do this. Well, we know that 1 mole is equal to 22.4 liters. And so now we're at the unit that we want, and we just have to solve for it. So 400 divided by 58.14 times 8 divided by 2 times 22.4, and it gives us 616.4430 blah, 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 one significant figure, so 600 liters of CO2. Oh yeah. All right, what I want you to do is I want you to try this one on your own and bring it to class, and we'll see how you did. Okay. Let's see. Okay, this is the last one. Okay, we'll do this last one together, and then we'll call it quits, okay? So we've got our balanced chemical equation, and don't always assume it's balanced just because there's coefficients. You do want to check, make sure it's balanced. All right, what mass of O2 results from the decomposition of 1 kilogram of calcium chlorate? All right, so we're starting with 1 kilogram of calcium chlorate. Okay, and we've got to go to grams of O2. So we've got to go from kilograms to grams to moles to moles to grams. Oh yeah. All right, here we go. Kilograms, CaClO3, 2. Just make sure you pay attention to your units at all times. All right, 1 kilogram is equal to 1,000 grams. That was easy. Kilograms are gone. All right, now we can go from grams, so we've got grams of CaClO3, 2, to moles. One mole is equal to 40.08 plus 2 times 35.45 plus 6 times 16. I think it should be 206.98. Okay, and then we've got 1 mole, whoops, not 1 mole, yeah, 1 mole of CaClO3, 2, and we've got to find oxygen, so 3 moles of O2, and then we're looking for grams, so 1 mole of O2 is equal to 32.00 grams of O2, and now we can solve. 1.00 times 1,000 divided by 206.98 times 3 times 32. And the answer gives us 463.812928 grams. We want 3 significant figures, so 464 grams of oxygen can be made. There you go. Okay, and that's stoichiometry in action, boys and girls. I know it's a lovely thing, especially for those of you that like numbers. All right, I guess I will see you in class.